You wake up to an alarm, catch a bus scheduled to the minute, and track your screen time down to the second. But imagine if, right now, every clock in the world blinked out of existence. Without a way to measure the hours, human civilization stalls. Ancient farmers needed to pinpoint planting seasons to survive. Traders had to coordinate bustling markets. Entire communities relied on specific times to gather for religious prayers. This presented early societies with a massive engineering problem. How do you physically measure something that you can't see, touch, or hold? The answer was to look at nature. To measure the invisible passage of time, you have to find a physical process that repeats itself with a steady, rhythmic pulse. By capturing those repeating natural processes, ancient people built the very first time machines. They engineered devices specifically designed to convert nature's endless loops into readable tools. Inventing the clock was about taking the wild, invisible forces of the natural world and translating them into a strict language of mathematics and structure. The most obvious repeating process in nature is the daily motion of the sun. To harness it, early engineers developed humanity's first major time machine, the sundial. Watch the sun arc across this diagram. As Earth rotates, the sun casts a shadow that drags clockwise across the board. The shadow is cast by the gnomon, the upright plate in the center. Its specific mathematical angle dictates exactly where the shadow falls. But there is a strict geographic limitation. Because the Earth is curved, a sundial perfectly calibrated to cast accurate shadows in Greece will give you the completely wrong time if you carry it south to Egypt. Look at this structure. This is the Samrat Yantra in Jaipur, India. Built about 300 years ago, it is the absolute pinnacle of shadow tracking engineering, standing 27 meters tall. Because of its sheer size, the shadow it casts moves about 1 millimeter every second. That allows an observer to read the time with an accuracy of up to 2 seconds. Yet, every sundial shares the exact same fatal flaw in its physics. The moment the sun sets, or a heavy storm cloud rolls in, this massive scientific instrument becomes a useless pile of stone. To gain true control over the hours, humanity needed a machine that ran independently of the unpredictable sky. The solution was to bring the repeating process indoors. Ancient engineers developed the water clock, like the early Indian Jalak Yantra, to measure time even in total darkness. Instead of tracking shadows, these devices tracked fluid. They measured the exact time it took for a specific volume of water to steadily drip out of a marked vessel, or for a tiny hole to slowly fill and sink a floating brass bowl. Look at this cross-section. Water introduces a problem: pressure. A full vessel pushes water quickly, but as the level drops, pressure decreases, slowing the drips. Furthermore, temperature shifts change water's physical properties. Cold water flows differently than warm water, ruining the clock's accuracy. Look at this hourglass. By swapping water for dry sand, engineers bypassed fluid pressure issues entirely. Sand falls through a narrow neck at a highly consistent rate, making it perfect for timing shorter, precise intervals. Building one required extreme calibration. Calibration is the meticulous process of adjusting an instrument so its measurements are exactly correct. In this case, sizing the glass holes so the sand takes precisely 60 seconds to fall. This reliability made the hourglass incredibly useful. In busy ancient Roman courts, they were strictly used to limit the time lawyers had to give their speeches. Meanwhile, other societies engineered the candle clock. By carving evenly spaced marks into a tall wax candle, you could measure elapsed time as the flame burned down past each line. Yet, like water and shadows, fire is temperamental. A slight difference in the wax mixture or a sudden draft of wind would cause the candle to melt unevenly, instantly destroying its accuracy. Mastering time was an endless evolutionary battle with physics. Every time early engineers solved one limitation of nature, they exposed a new physical variable they had to invent a way around. Despite their individual quirks, the sundial, the dripping water vessel, the falling sand, and the burning candle all succeeded at the exact same goal. They successfully converted the repeating processes of nature into readable, measurable data. And that ancient engineering mindset is directly connected to the modern technology sitting in your pocket right now. If you open up a modern smartphone or a digital watch, you'll find they still rely on a repeating physical process. Today, we measure the hyper-fast, precise vibration of a tiny piece of quartz crystal when an electric current runs through it. We have upgraded from dripping water to vibrating crystals, but the core physics principle of the time machine remains identical to the ones used thousands of years ago. This relentless observation of the physical world and the drive to manipulate it laid the groundwork for all modern engineering. It also set the stage for the next massive historical leap in timekeeping, a brilliantly simple device utilizing gravity and a swinging weight. The long quest to measure the hours proves that by carefully observing the natural world, human beings can engineer solutions to the universe's most invisible challenges.